Explainable zero-shot food categorization using visual language models. This work was presented as a poster at the CVPR 2025 MetaFood Workshop. In this project, we ask a simple but demanding question. Can we classify complex real-world food images into fine-grained classes with no task-specific training? And we also provide a clear and human-readable reasoning path for each prediction. Classic food recognition pipelines rely on supervised models trained on datasets such as Food 101.g. They usually stop at reporting accuracy and do not expose their internal logic. Modern vision language models such as BLIP-2 and large language models such as ChatGPT enable zero-shot classification. They use broad pre-trained multimodal knowledge instead of task-specific learning on Food 101. However, these zero-shot systems often behave like black boxes. This makes it hard to debug mistakes, refine prompts, or build user trust. Our contribution is a two-stage pipeline that exposes an interpretable textual reasoning trace. It links each image to its final Food 101 label in a transparent way. We first interrogate the image with BLIP-2 using a structured set of questions. Then ChatGPT reasons over the answers and selects the most likely food class. This gives us both strong accuracy and explicit transparency. Food image understanding is central to many practical applications. Examples include dietary monitoring, health analytics, recipe search, and restaurant automation. Supervised CNNs and transformers trained on Food 101 work well when training and test domains match. They struggle with new dishes, novel plating styles, and noisy images without costly retraining. Vision language models such as CLIP and BLIP-2 learn joint visual and textual representations. They support zero-shot classification through prompt design and cross-modal matching. Large language models such as ChatGPT can perform rich reasoning over text alone. Our idea is to combine these tools while exposing the intermediate reasoning steps. Instead of asking one model what dish is shown, we split the process into two stages. First, BLIP-2 acts as a visual question answering engine focused on food. We ask a domain-specific ordered list of questions about each dish. These questions probe if it is a dessert or main course, sweet or savory, soup or salad. They also ask if it looks like pasta or rice, a burger or a sandwich, and so on. Second, we pass the resulting question and answer transcript to ChatGPT. We include the full list of Food 101 class names in the prompt. ChatGPT is instructed to select exactly one label that fits the transcript. This yields a simple but powerful pipeline. It goes from pixels to structured question and answer text to the final label. Every step is expressed in human language and can be inspected. We evaluate our approach on the Food 101 dataset, a standard food benchmark. Food 101 contains 101,000 images across 101 categories. Each class has 1,000 images that cover a wide range of dishes. Examples include apple pie, cheesecake, ramen, paella, and spaghetti bolognese. The standard split provides 75,750 training images. It also provides 25,250 test images. Both splits have balanced counts of 750 or 250 per class. Food 101 is intentionally challenging for recognition models. There is high intra-class variability in plating, lighting, and ingredients. There is high interclass similarity between some pies, cakes, and pasta dishes. Background clutter, such as utensils and restaurant scenes, is common. There is also non-trivial label noise in some images. Food 101 was designed for supervised training of deep models. In our work, we used it purely as a zero-shot testbed. BLIP-2 and ChatGPT are not fine-tuned on Food 101 images or labels. They only receive the list of category names as text in the prompt. This setting reflects realistic deployment scenarios in new food domains. We want to avoid collecting and annotating thousands of images for each new class. Our task is to assign one of the 101 labels to each test image. We do this using only pre-trained models and carefully structured prompts. In stage 1, we use BLIP-2 as an interpretable visual interrogator. We do not ask BLIP-2 to directly name the dish in one step. Instead, we treat it as a visual question answering system. Each image is paired with a fixed set of 39 domain-specific questions. Questions are ordered to mimic how a human might reason about food. We start with broad, high-level properties of the dish. We ask if it is a dessert, an appetizer, or a main dish. We ask if it looks sweet, savory, or possibly both. Next, we move to preparation and serving style. We ask if the food seems raw or cooked, baked, fried, or grilled. We ask if it resembles soup in a bowl, salad on a plate, burger, or sandwich. Then we inspect finer structural cues of the dish. We ask if it looks like noodles or pasta. We ask if rice is a main component, or if it seems layered like lasagna or tiramisu. Later, questions probe for explicit dessert signals in the image. These include icing, cream layers, fruit toppings, and powdered sugar. We also ask about visible ingredient cues, such as tomato sauce, cheese, and meat. Further questions check for shellfish, leafy greens, or eggs in the dish. We ask about hints of specific cuisines, such as Italian, Japanese, or Mexican. Shape cues like taco folds and dumpling wrappers are also queried. For each question, BLIP-2 returns a short, natural language answer. Examples include that the dish appears savory, or that a red tomato-based sauce is present. It may say that long noodles with meat are mixed in the plate. All question and answer pairs are stored as a textual log for that image. This log is an explicit human-readable description of what BLIP-2 believes it sees. It forms the key bridge between vision and high-level reasoning in our pipeline. In stage 2, we pass the BLIP-2 question and answer log to ChatGPT. We turn ChatGPT into a reasoning-based food classifier. The prompt we send to ChatGPT has 3 main parts. First, we include a short instruction that describes the task. For example, we say that it will see answers about one food image. We tell it to choose one food, 101 category, that best matches that image. Second, we include the complete list of food 101 class names. Third, we include the full sequence of questions and answers from BLIP-2. ChatGPT must then select exactly one label from the list. We may also ask for a brief justification of the choice. Consider an image of spaghetti bolognese as an example. The log might say that the dish is savory and has long pasta on a plate. It might say that a red tomato-based sauce is present and that meat is likely mixed in. From these cues, ChatGPT can infer that spaghetti bolognese is the best match. It will prefer this label over plain spaghetti or pizza. This design separates low-level visual parsing from high-level reasoning. BLIP-2 handles image perception and ChatGPT handles semantic inference. The pipeline also yields a transparent chain of evidence for each prediction. If the final label is wrong, we can inspect the earlier steps. We can see if BLIP-2 misread visual features, such as melted cheese or icing. We can also see if ChatGPT misused otherwise correct cues from the log. The system is therefore explainable, debuggable, and modular. We can refine the question set, change the label space, or swap in another vision model. The core logic of how the reasoning trace is used remains unchanged. The design of the 39 questions set is crucial to our method. We organize the questions into functional groups that narrow the label space. Initial questions act as course filters over the domain. They separate desserts from main courses and sweet from savory dishes. This early step removes many obviously incompatible classes. Mid-level questions focus on shape, serving style, and main components. They ask if the dish looks like pasta, rice, soup, salad, burger, or sandwich. They also query for tacos and dumplings to cover specific food families. These questions allow us to rule entire groups of classes in or out. Later questions are highly category specific and focus on key visual details. They look for layered pasta that might signal lasagna. They look for whipped cream and strawberries for cakes and shortcakes. They check for powdered sugar on a grid-like surface to detect waffles. They query for raw fish slices that suggest sashimi. The final question asks BLIP-2 to guess a food 101 class directly. This gives us a direct comparison between BLIP-2 and ChatGPT decisions. To test the benefit of the full pipeline, we add two simple baselines. The first baseline is a generic vision language model for direct classification. It receives the image and the food 100M on the list and must pick a label in one step. This model often defaults to generic classes, such as cake for many desserts. It has trouble with subtle distinctions between visually similar dishes. The second baseline is a single prompt ChatGPT setup. Here, the language model sees only a short text description of the image. It must guess a class without detailed structured question and answer context. Without a dedicated vision encoder and rich prompts, its performance drops. In contrast, our BLIP-2 plus ChatGPT pipeline performs much better. We evaluate it in a zero-shot setting on the food, 101 test split. It achieves a top 1 accuracy of 96.5%. This modestly surpasses recent large-scale, zero-shot approaches on the same task. At the same time, it produces detailed textual explanations for every prediction. From a qualitative point of view, the system often behaves in a human-like way. This was clear in the example shown on our MetaFood 2025 poster. For correct classifications, the question and answer logs read like careful descriptions. A pizza image yields mentions of a round flat base, tomato sauce, and melted cheese. It also lists toppings that match the visual details in the image. A tiramisu image leads to notes about layered dessert, cream, and cocoa powder. It may also mention a hint of coffee flavor based on typical appearance. A ramen image triggers comments about broth in a bowl and long noodles. It may also mention slices of egg or meat floating on top. For misclassifications, the logs reveal clear failure modes. The model may claim that a white sauce looks like icing and suggest cake-like dishes. This can push ChatGPT toward dessert labels instead of pasta labels. In other cases, BLIP-2 may fail to notice rice grains in the bowl. It may then describe the dish in generic terms that fit several pasta classes. These transparent traces give us concrete levers to refine the system. We can adjust prompts, reorder questions, or add new ones to remove ambiguity. We can also inject light domain knowledge in the form of simple rules. Such rules can help reconcile conflicting cues in tricky cases. In summary, explainable zero-shot food categorization using visual language models shows a clear result. It is possible to combine state-of-the-art zero-shot performance with a fully inspectable reasoning chain. We achieve this by orchestrating a vision language model and a language model through a question interface. Future work will explore automatic discovery and tuning of question sets. We also plan to integrate structured food ontologies and nutritional information. Another goal is to extend the pipeline into richer conversational food agents. Such agents could label dishes and also discuss ingredients and cooking methods. They could support dietary queries in an interactive and transparent way.